Hello everyone. In this video, we're going to start talking about kinematics. So we're going to get into real physics for at this point. In the past, we just did we looked at some of the tools we're going to need for physics. We looked at some trig. We looked at some vectors. Those are good math tools or necessary math tools to have. So here today, I'm going to talk about this idea of kinematics. Okay, and what kinematics is just the study of motion, okay, without paying attention or without caring about what caused that motion. So in other words, you are describing the motion either with the graph or with the mathematical equation. So if something is going at a constant velocity, we have to maybe graph the data and prove that it's a constant velocity. If it's speeding up, we have to prove that it's speeding up. But we really don't care about why it's going at a constant velocity, or why is it speeding up, or why is it slowing down. So the kinematics is basically just the study or description of motion. Two big concepts in kinematics are velocity and acceleration. So I'm going to start talking about velocity. Now, and speed. Speed is just how much distance you travel in a certain amount of time. It's the ratio of those two. So V, and I'm going to do the average speed, because that might be changing during your travel. You might be going slower, faster. So the average velocity, I put a line over it, is basically just total distance over total time of travel. This is the whole distance traveled, and this is the whole time or the total time that it took you to cover this distance. Now, at times you might be covering less distance or more distance in equal amounts of time, but I'm just looking at the overall. So I'll do an example. So let's say Brian walks 30 meters at 2 meters per second. And then he jogs, here he walks 50 meters at 4 meters per second. Now, and the question is, well, find the average speed, not even velocity, speed, which is a scalar quantity. We're just looking at how many meters he covers per second on average, not at every moment. So we can't just take the 2 and the 4 and divide and add them together and divide by 2. So we have to go back to the definition. So the average speed, you have to find the total distance, which is really 80 meters, divided by how long it took to do this 80 meters. Well, you can use the average velocity equation for the different phases of the problem. So this is going to be just 30 over 2, and the other one is going to be V2 equals 50 over 4. So I made the numbers easy. So this should give us 15 seconds. This should give us 12 and a half. So that's 27 and a half in total. And that should give us, I think, 2.91. See, it's not 3. And that's meters per second. You must put your units. Okay. Now I'm going to talk a little bit about velocity. Okay. Velocity with an arrow on it indicates that it's a vector quantity, which means it's magnitude with units, of course, and direction. So this is going to be displacement over time. Well, what's displacement? Displacement, is the direct line that connects your starting point to your final destination. So if you're walking east, you're going 10 degrees north of east, then you decide to go north, then you decide to go south, and then from here you decide to go west. Okay? The displacement is just the link between these 2 points here. Okay, divided by how long it took to do this whole trip. Okay. So let's do a problem with that. And by the way, when it's one-dimensional, the velocity, meaning like we're not going off at an angle, it's just going right and left or up and down. The velocity in one dimension, in 1D, is just basically equal to the change in your position over time. So when you're looking at the position, just think of the number line. So just think of it as like you're walking back and forth along a number line with 0 and negative numbers and positive numbers representing your position with respect to that origin, that 0. All right, so let's do a problem. So I'm going to say, you know what, Matt runs 4 miles west for 30 minutes. He then makes a 30-degree right turn from his perspective and continues for 2 miles for an additional 12 minutes. Now he's going faster, it looks like. What's his speed and what's his velocity in miles per hour? So let's see if we can do that. Speed, I think, is easy. So you just have to take total distance, which is what, 6 and over 42 minutes, but you have to change 42 minutes to hours. So you just do 42 divided by 60. So that's an easy one, right? So that's going to be average speed is 6 divided by 42 divided by 60. And you get your answer. Now let's see how we can get the velocity. That's where it gets a little tricky. And this is not one-dimensional because he goes off at an angle. So he's going west. Okay? And then he makes, so he's going in this direction. He makes a 30-degree turn from his perspective. So he's going to be going north of west. Right. So this distance here is 4 miles. This distance here is 2 miles. And we're going to try to find this displacement. And once we find this displacement, I'll call it D. I'll divide it by 42 over 60. In other words, 42 minutes changed to hours. Now the question is, how do we find this D? Well, you can do this a couple of ways. You can do it with the chart method. You can break down the 4 miles into components. So it's going to be, its x component will be -4, its y component will be 0. And you can break down the 2 miles into x and y. The x will be negative since it's pointing left, and the y will be positive. Or if this is 30, this is 150, okay? And you can find, you can do law of cosines, and you can find this D, which I'm not going to do. You can do that on your own. And once you finish, you do law of sines, or you repeat the law of cosines, and you can find that angle. Just make sure when you're doing this, the triangle makes sense, because remember, if you're doing law of sines, this angle, the possibilities for these angles is an angle under 90 and its supplement. Okay, we talked about that in class. Another way we can represent or find the velocity, okay, is graphically. So let's just say I plot my position. I can call it P, or you can call it X, and versus time in seconds. This could be in meters, it could be in miles, this could be in hours, it doesn't matter. So I'm not starting at the origin. In other words, when the time starts, when the clock starts here, I'm already past the 0 on the positive side, on the imaginary number line that I'm talking about. So if I do this, okay, I can see that my change in x over change in time is nothing other than the slope, which means if you have a position time graph, the slope gives you your velocity. Okay? This means that I'm going in the positive direction. And how do I know that? 2 ways to know that. Your slope is positive, which means your velocity is positive, or you can see that your position is increasing. So you're going from low numbers on that number line to higher numbers. I can do something like this here. This just means that I started some number on the positive side and I'm going in the negative direction. I don't have to get back to the origin. You can start from down here. Okay? Okay. Now, another way of representing velocity, or at least when velocity is not constant, for all of those, the velocity is constant because the change in position over time remains the same all the time. If I have a graph of position, so I'll just call it x, or you can call it p. It doesn't matter. Time, seconds, meters, miles, inches, whatever. So if I have a graph that looks like this, okay? Okay, this means that I started, when the clock started, I was behind the zero, behind the number line. So if your number line is here, so that's 0, 1, 2, -1, -2, you probably started on this side, where, I don't know, if this is -1, this is -2, I started somewhere in between. And then it looks like my changes in x over time, over the same amount of time, are getting bigger and bigger as the time passes. This tells me that I'm speeding up. My velocity is getting higher and higher and higher. So how do we know the velocity from a position time graph? We just look at the steepness of this curve. See, for a line, the steepness remains the same no matter where you put yourself on the line. But for a curve, the steepness changes. And this is how I do it. I say, well, this is not so steep, but as I travel up the ramp, it looks like I'm getting steeper, not the ramp, but you know what I mean, up the curve. Okay, so this is going to be our first video. This is going to be called Kinematics 1, and I'll do multiple videos for kinematics because it's a big unit. Have a good night.